Okay, so yesterday we did the previous question about the mixture of acids. Now we need to talk about percent dissociation. We would never talk about percent dissociation for strong acids because they're 100%, but weak acids we would be looking at that. So the way that we would do that is we would have to figure out how much was actually dissociated, so we'd have to figure out the hydrogen content. And so if we were going to do that for this first one, we don't even need to do the rice table. We can just say that it's given us the Ka value. So we would say 1.8 times 10 to the negative 5 is going to be equal to x squared over 1. Because we are going to be able to neglect x, so we know that that's what it's going to be. So when we solve for x, we would get that x is equal to 0.0042. Okay. It doesn't ask us to do the pH, but let's go ahead and do the pH just to see where we're at. Negative log, and that's going to be equal to our hydrogen concentration. So negative log of 0.0042. So our pH would be 2.38. Again, that's not part of the question. Let's just add that in there so we can kind of see where we're at. And then to get the percent dissociation, how do we find the percentage of anything? Part over whole times 100. So our part is our hydrogen concentration of 0.442. What is our whole? The original concentration, 1, and then times 100. So we would have 0.42% dissociation, which is not very much, right? So that means only 0.42, I mean, that's not hardly any dissociation, so it's very weak dissociation. If we were going to do it for the other one, same concept, 1.8, I'm doing a different color, times 10 to the negative 5 is going to be equal to x squared over 0.1. And when we solve for x there, we get x is equal to 0.0013. Okay? If we were to do the pH of that, it ends up being 2.88, not a huge difference in our pH, but look what happens to our percent dissociation. It goes up quite a bit because we would do 0.0013 divided by 0.1 times 100, and that would give us a 1.3% dissociation, which is still not very much, but it's basically 3 times as much dissociation. So something that could show up on a multiple choice question is that the lower your concentration, you actually get a higher percent dissociation. So that was the difference between 1 and 0.1, and we went up quite a bit on our percent dissociation. Still very small, but definitely an increase. Okay, so that's a quick and easy multiple choice question. If they were to give you several weak acids of different concentrations, you could calculate that and know that the lower the concentration, the more percent dissociation you have, or the higher one. Okay? Does that seem pretty easy? Okay. You can also, on our next problem, you can calculate Ka from the percent dissociation. Okay? So the next problem, 14, says lactic acid. It's what you get when you exercise. If you have a 0.1 molar aqueous solution and it is 3.7% dissociated, calculate the Ka value for that. So we would write that as x. I don't like that color. It's not showing up very bright. X over 0.10 is equal to 0.037, because we want to take it out of that percentage, right? So then x is going to be equal to 0.0037 molar. So then we could plug that in for our Ka value, because remember we're going to have H plus times, that one would be the C3H5O3 over the H, C3HO5. And I'm just getting that from dissociating that. I should have probably written that first, sorry. So it dissociates this way. We just take off one of the hydrogens. So now we can plug in because we know everything. So we know that H is 0.0037. Because it dissociates 1 to 1, what is the concentration of the lactate? This part. Also 0.0037. And then it gave us the concentration, which was 0.1. So our Ka value would end up being 1.36 times 10 to the negative 4. Any questions on how and why I did that? Oh, because this, I'm plugging this into part over whole for the percent dissociation. Yeah. So because I know the formula is hydrogen concentration over the total concentration of the acid times 100. So I was just plugging that in. So it's not, I'm not plugging it into the Ka. So that's why it's not x squared. And then, of course, because it dissociates over here 1 to 1, then it would be whatever you got for hydrogen is also the concentration for the, I guess that's called lactate. I don't know. I don't know what that is called by itself. If it's acetic acid and goes to acetate, I'm assuming it's lactate. I don't know, but I don't like, that's not a good word to use. Yeah. Never mind. Okay. It's a tough crowd today. All right. So here we're going to do pH for Kb. Very similar. Down we're just using the Kb values. But when we want to go to pH, remember what we get is going to be a hydroxide. So we're going to get a POH, so we have to remember to subtract it from 14. That is a very common mistake is on a test because you're so busy working it and you're so excited to get a concentration that you just take the pH of it and then you're like, I'm done. But it's a POH. Okay, so make sure you know when you're solving for Kb, you're getting a hydroxide concentration. Not a bad idea to write that down somewhere and say hydroxide concentration. Remember to subtract from 14. Okay, so here we're going to calculate a pH for a 15 molar solution of NH3, and it gives you our Kb value. Did you notice the Kb value for ammonia is the same Ka value as for acetic acid? It's weird. So they're actually pretty easy numbers to remember. I don't know why they're the exact same, but they're totally different. So we're going to go back and do the rice table just so we can refresh our memory. So NH3, we're assuming the water is there. We can put it in there if you want. That way you know where the hydroxide comes from. It's going to give you NH4 plus hydroxide minus. Okay? 15 molar, that is really strong, so we will definitely be able to neglect X because that's going to not make a difference when we get our dissociation. We don't care about water, and of course this is 0 and 0, so rice change is going to be minus X plus X plus X. So at equilibrium we have 15 minus X and then X and X. So Kb, which is 1.8 times 10 to the negative 5. So we're going to do x squared over 15 minus x, and then I'm going to go in and say neglect.
When you say you can neglect an x, can you put it right next to the pH too? Can you just be like, neglected the
Oh, wait, can you, that thing is just cut off and I couldn't hear you. What?
Okay, so whenever you say like you neglect the x, can you say that earlier in the problem? Like
You could have set it up here. You could have circled it here and said neglect here. Either way. I just like to put it in the problem so that the reader knows that, hey, I knew it was supposed to be there, but I'm saying I'm going to neglect this. Yeah. But don't just like let it disappear. Say something. Say assume negligible or neglect so that they know what the process is. Yeah. Otherwise they think, oh, they just dropped it off for no reason. Fell off into the earth. Okay, so then when we do our math on that, we get x is going to be equal to 0.0164. But remember, that is our hydroxide concentration now because we're dealing with the base. So we would take the negative log of the 0.0164 is going to be equal to 1.8, which is equal to our POH. So pH is 14 minus 1.8. So our pH ends up being 12.2. And that's a way you can check yourself, because whenever you see this problem and it's telling you to calculate a pH, you know that ammonia is a weak base, so you should get a pH of above 7. And if you get to the answer and you're boxing something that's below 7, that should be your clue that, wait a minute, this is a base. What I calculated was a POH. And then remember to, I can't tell you how many times people forget to subtract from 14, and so then they get that part wrong. Okay? All right. I want you to do exercise 16 on your own, and we'll come back together and see if you do it correctly. So I'm going to freeze that and pause the video. Okay, so hopefully you got 12.3. Technically it should be 12.30 because we had two significant figures up there, so it should be 12.30 technically. Okay? All right. Now we're going to talk about polyprotic acids, because if you remember, I think it was the first day of notes, we said that when acids lose a hydrogen, if it's diprotic or polyprotic, they do so one at a time. So they're literally contributing their hydrogen one at a time, and each one of the species after it loses one hydrogen has its own Ka value. So we show it like this: Ka1, which is the first dissociation, Ka2, which is the second, and Ka3, which is the third dissociation. And if you look at their numbers, you see that the last one is a much smaller Ka value, so it has less, so it contributes a lot less to the pH than the first one. So the next problem that we're going to do is going to take up a lot of room, so you should write really small. And that's just listing the Ka values. So here we go. We're going to do the pH of 5 molar phosphoric acid, which is a weak acid. And we want to know the equilibrium concentrations of the species at each one of those. Okay? So this is going to take a while. So write small. Okay. So first thing we need to do is the first dissociation. And so we have, on the previous page, we have those Ka values, so we're going to have to flip back and forth a little bit. Okay? So we're going to start with the first dissociation, which is the H3PO4 dissociating to H2PO4, which is going to be minus plus H plus. So we're going to have 7.5 times 10 to the negative 3 is going to be equal to x squared over 5 minus x, neglect. Okay, so we get x is equal to 0.194 molar. Okay. So once this happens, we can figure out our H3PO4 concentration once they start dissociating is going to be equal to 5 minus 0.194. So that's like 4.8. So I'm going to circle that in red because that's the first equilibrium concentration we need. Okay? Of course, we know that X, we said, was equal to H plus, but in that first dissociation, what is it also equal to? The H2 PO4 minus. So that concentration is H2 PO4 minus, and it is 0.1. We're just going to go with 0.19 molar, 2 decimal places. So that is our second concentration that we need. All right, so now we'll do the next dissociation. We'll do it in purple. So we have H2PO4. It's going going to lose, which is a minus. It's going to lose another one, and go HPO4 2 minus plus H plus. So this one we should do a rice table for, so we can keep up with it. So this is going to be, we know it's going to start out at 0.19, 0, but this is also going to start out at 0.19 because we have it from the first dissociation. So minus x plus x plus x. So this equilibrium is 0.19 minus x, x, and then 0.19 plus x. Okay? We're going to assume again that we can neglect x to make our life easier. So we're going to neglect it here and here. Are y'all with me on that?
Yes.
Thank you. 6.2 times 10 to the negative 8, that's the Ka2 value, is negative, is equal to 0.19. We do not know this concentration right now. We could put x in there, but we're just going to leave it as that, so when we get done we can just know what that is, over 0.19. So when we do that math, we get the concentration of HPO4 2 minus is equal to 6.2 times 10 to the negative 8. I changed colors, but there's our third concentration we need. So we can figure out the last one. We don't even, it's going to be very negligible, so we don't necessarily, I lost my calculator. Okay. So to get the last one, for the phosphates, the only thing we're missing now is the phosphate concentration, correct? So for that one, we're going to do Ka3 is going to be equal to the H plus the phosphate, or not plus, times the phosphate. I'm running out of room, sorry. Oh, you're freaking kidding me. Ah! It totally disappears. I can't. I got too close to the edge. Hopefully you have all that written down so far. I apologize. I got too close to the edge that makes the page move, and I can't get it back. So, hopefully you have all that written down. Yeah. So we have H plus, PO4, 3 minus, over the HPO4, 2 minus. So we plug in the Ka value, 4.8 times 10 to the negative 13. That's the published value. And then we're going to have 0.19 because we still, our H is pretty much 0.19 the whole way through because the most of the hydrogen is coming from the first dissociation times the, no, not that one, hold on, PO4, the phosphate. I am so sorry that went bye-bye. And then we plug in the concentration we got a while ago for the HPO4. So we find our phosphate concentration to be 1.6 times 10 to the negative 19. So not very much. And then we need the pH. So what is the pH? Negative log of the hydrogen concentration, which we found to be 0.19. So it should be pH is equal to 0.72. So again, I will take you back to don't confuse strength of acid with concentration. A phosphoric acid is considered to be a weak acid, but that's a really low pH. So don't think just because it's a weak acid that it's going to have necessarily a really high pH. Happens to be a fairly concentrated, 5 molar, happens to be fairly concentrated, but you still have to make sure you understand those differences. Now let's pause and ask questions, if anybody has questions. Did you understand the process? Was there any point at which you got a little confused or lost? Because now would be a good time to ask a question. Okay. Oh, are you stretching? You do have a question? Yes.
So they'll give us the Ka value?
Yeah, you never have to memorize Ka values. There's too many of them. Yeah, you will always be given a Ka. Sometimes you might be given a Ka and need a Kb, but I'm going to show you how you could get to the other, right? Okay. How could you get to the other? But Kw, by using Kw. Okay, so I want you to do sulfuric acid on the next one. I want you to try that. So I'm going to pause the video. So if you do the math, that's why. Because the second dissociation is only going to give you 0.012. And when you take, you have to add them together to get the concentration. So you need to know how to do this, because if it asks you what the concentration of hydrogen was, if you did 1, that would not be correct, but 1.012, because the amount of hydrogen from that second dissociation would be added to the amount for the first one. Now for phosphoric acid, those Ka values are really, really low, so it wouldn't make a difference, but on this you would do that for the concentration. Any questions on that one? If you did the, yes?
But an overall technique of working this out, it wouldn't matter whether it's a strong acid or a weak acid, you work it the same.
So yes, if you were doing it this way. But the difference for the strong acid is most of your hydrogen is coming, well, even for both of them, yeah, you're right.
I just...
Yeah. And only if it's a strong acid that's diprotic. So like you wouldn't do this for any of the other strong acids, because H2SO4 is the only strong diprotic acid. The rest of them are monoprotic, so you would just take the negative log of the concentration. So H2SO4 is like the exception to those strongs. Yes, ma'am?
How do we know the initial concentration of hydrogen?
It's 1. Because it's a strong, the first dissociation is strong dissociation, so it's 100% dissociation. So it's 1. Yeah. And the HSO4 is also 1. I just didn't write it down because it's a 1-to-1. So that's how I knew that HSO4 minus was a 1 as well. Because the first dissociation is 100%. Were you wondering where that 1 came from right here? That's where it came from. I just didn't show it, but this would be 1 and 1 because of its 100% dissociation. Okay? All right. Getting very close. Now I want you to do the next one, which is number 19, which is sulfuric acid, but now we're dealing with a weaker concentration. So I want you to try that as well. Because, did it leave that one out, or did I just hit it too much? Number 19 got left out of my PowerPoint, but you have it in your notes, right? Try number 19. What time is it? We're not going to make it. I thought we could finish the notes. Shoot, I really needed to finish today. Oh, I thought I paused the video. Okay, so exercise 19 should look like this. The first dissociation, of course, we get the 0.01. So when we do the second dissociation, we plug in our Rice table, and I realized very quickly that the 0.01 is too close to the Ka value of 1.2 times 10 to the negative 2. So it was definitely over 5%, so we are going to have to use x in our calculations. So when we put x in, we keep x into our calculations, we have to do the quadratic formula, and when we get the answer to the X, we get 0.0045. So for the second dissociation, the hydrogen that's contributed from the second dissociation is 0.0045. We add that to the 0.01 from the first dissociation, and we get a new hydrogen concentration. And when we take the negative log of that, we get our pH is 1.84, which is definitely lower than the 2 that we would have done if we just had used the first dissociation. Now, what's the difference between this exercise 19 and exercise 18, where the second, in exercise 18, the second dissociation did not make a difference, and it has to do with the concentration. Remember from the beginning of the lesson, we talked about the percent dissociation being higher for smaller concentrations, and this is 0.01 versus 1 in the other one, which is a much lower concentration. And so the second dissociation does contribute enough of a concentration that it does make a difference in the pH. And so that's how you do that when you have a lower concentration. All right, that concludes the lesson, and see you next time.